Welcome back to Workplace 30. We're on to 6.1, which is titled Single Transformations. You can start by reading Math on the Job on page 216 and then checking in for the following questions. Question 1. The bottom of the dado will be cut from 0 to 1, which means your x-coordinate is 0 and your y-coordinate is 1, to the point, again, x-coordinate is 12, y-coordinate is 1. And then the top one will be cut from 0,19 to 12,19. So actually what I did here, mine's a little bit off, but this point here would be the point 0 and 1, and this point here would be the point 12 and 1. Then here, this point right here would be the point 0 and 19. This point here would be the point 12 and 19. So they need to install 2 more cuts in between here. So the first thing I did is I figured out that the distance between 19 and 1 was 18. And 2 more cuts would mean splitting it into 3 parts. So 18 divided by 3 is 6. So each one of these cuts needs to be 6 units apart. So I started here and counted up 1, 2, 3, 4, 5, 6 to my next cut. That cut will also go to 12. Ooh, some of these are a little bit off. 12 would be about there. So these should all be to 12. Right there. Is that working? Oh no, it's just changing that. There we go. So those would be till 12. You need to find the coordinates then of each of these. So your first coordinate here would be 0 and 7 because it's 6 units up from 1. So that gives you 7. The other side, it's again 6 units up from 1, so it gives you 7 on the y, but your x coordinate here is 12. So go ahead and try for this last one and check to make sure you got the same answers as I did. Question 2 says, if you went through your first cut and ended up right here, then you need to get all the way back to your starting point of your next cut. How far would you have to move? So how far left and how far up? So you'd need to move 12 left and then 6 up to get back to that starting point. So that's what is written here. Then you can read Explore the Math on page 16 and copy the following definitions. Note that translation also means slide, so that's just taking a shape and moving it. And if I create just another page here, I'll show you what this means. So if I just create some kind of shape, it doesn't matter what shape, the first thing I'm going to do is move the shape or slide it. So I can take this shape, move it here, there, it's been translated. Move it back, it's been translated again. The next, where are we? Next is the rotation. So if I select this object and then the green and I just rotate it, that would be a rotation. There's also a reflection. So if I were to create a dotted line somewhere through the center of this, and then I'm going to flip it, that would be a reflection around that line. Now I could create a different line going horizontally through this. And again, if I flip the shape, it could be flipped around that line also. Then let's look at example 1 on page 217. We have a supervisor for an active logging site, and the current site is shown here in red. He wants to move this to a new site, and all he knows is that vertex D should be moved to the point 15 and 4. So then we need to adjust the rest of the points accordingly. So let's start by looking at point D. When we moved it from 6 and 2 to 15 and 4, our x-axis changed by 9, and positive 9, and our y-axis changed by positive 2. So if we would just add those numbers onto the x and y coordinate of each of the other vertices, we'll get our new vertices. So for example, point A, we have a 2 and an 8. So the 2 we need to add 9 to get 11. The 8 we need to add 2 to get 10. Same with B. We need to add 9 to get 15, and we need to add 2 to get 10. That will translate our shape to our new area. We're going to do activity 6.1, find the perfect match. We're going to look at these diagrams, identify which yellow shape is the perfect translation of the green shape. Then we're going to find the vertex of each original and each translated image and identify how many units of shape has been translated. Now the first one here is done for you. Your original is the green. We determined that shape number 2 is the translated shape because if you count 16 units left and 4 units up from every one of these corners, you will be moved exactly to where shape 2 is. So shape 2 is our shape, is our translated image. Shape 1 then we'll go through and find the vertices, same with shape 2. They're shown right here. Then we need to determine how many we moved over and how many up. So you could have done that by counting. You could also look at, for example, this point. So the difference between them is 16. And here the difference between these is 4. So that tells you that you moved over 16 and up 4. Try the next one on your own. Next, using graph paper or this graph paper on your handout, draw a shape on the coordinate plane and then draw 3 transformations of the shape, but only make one of them a perfect translation. So for example, if I make a right triangle, now it's easier on the smartboard, I know. But if you choose, there is a web application listed here that you could also do this with. So I am going to clone this triangle and then take one of those triangles and shift it somewhere else. So that would be a perfect transformation. But if I take a different triangle, a different clone triangle, I'm going to enlarge it a wee little bit. Okay, that would not be a perfect translation. I could also take one more triangle, enlarge it a wee bit, and turn it. Okay, that would not make it a perfect transformation. So this one would be the perfect transformation. Discuss the ideas, reflecting letters for printing. So if you look at a rubber stamp, you'll notice that it looks backwards. We're going to write or print out all the letters of your name in uppercase. And then you need to make a line of reflection. Try then flipping these to make mirror images on the other side. So again, with the smartboard, I could flip this and it should be reflected like that. So N would be reflected like that. I would say the same. C would look backwards, O would be the same, L would look backwards, and E would also look backwards. Give it a try. Now for question 3, which of these look the same, whether they're written forwards or backwards? So that would be the I and the O. Would changing the font change this? Yes, it would. For example, if some font might have an I kind of like this, whereas another one would just be a big block letter. Those would look different than when they're reflected. Do they look the same when they're reflected horizontally? So to do this, I'm going to take the L and the N from my name, and I'm going to flip them. So that one changed from a regular L to an L like that, and the N changed from a regular N to an N like that. So the N's here, if you notice this N and this N, those actually have not changed between vertical and horizontal. However, some letters will be the same as they appear. For example, I would be the same if it was reflected horizontally. Also, the letters like K would be the same as reflected horizontally. What other letters can you find? Example 2. Cameron is printing a window decal. The sticky side is on the front so that you can stick it on the inside of the window, but you need to be able to read the sticker from outside. So he needs to create a mirror image of what the sticker is supposed to look like. Which axis of symmetry would you do this over? So again, if you flip this, you'd end up with a tree that was like upside down like this. Ooh, that's a really bad drawing. However, if you flipped it to the side, you'd end up with a tree that was still right side up. So let's try that. So we know that this is 2 over, so our next point will be, again, 2 over. F is 1, 2, 3, 4 over, so 1, 2, 3, 4. And G is 6 over, so 1, 2, 3, 4, 5, 6. So there's the top of our tree. And they go in 1 and down again 3. Back in 2 and then make your stem. So there we have the tree, which was rotated over the y-axis. Then try to draw this on your own. Last but not least, we have mental math. How many lines of symmetry do the following shapes have? So if you make a rectangle, this rectangle would have 2 lines of symmetry. It could be flipped vertically or it could be flipped horizontally. A regular pentagon is slightly different. This pentagon could be flipped on any one of its 5 axes. Ooh, that one's a bad one. And it would look different. The rhombus would have 2 axes of symmetry on its diagonals. The kite would only have 1, right down the middle. That's where it's still symmetrical. And the equilateral triangle would have 3. Last but not least, you have an assignment on page 226, number 1 to 4. Enjoy.